In this video, we will present some results from Smig use case 2, Digitized material tracking. The system for digital material tracking provides a platform for the data analytics which are required for mine-to-mill optimization. Mine-to-mill optimization is a well-known problem with high potentials. If done right, typically in order of 10% of increased production. The project consists of 3 work streams. The aim for the project was to show how digital tracking system can be implemented and used as a part of the Smig infrastructure.
Material tracking starts at the very beginning of the mining process in the exploration phase, looking for a mineral with high ore concentration. However, the time scale of exploration activities are long compared to the time scale of the mining production phase. The mining phase, a constant flow of material from an unbroken ore body, is stepwise refined into its end product, for instance, copper or iron. We will here show how the data generated from the drill rig can be used to generate value with a material tracking system in the ore excavation process. It all starts with drilling blast holes in the ore body, which are charged with explosives and thereafter fragmented into rock particles by blasting. The resulting pile of fragmented rock is thereafter loaded for transportation. Previous investigations in the Aitik mine shows that the shovel fill factor is clearly correlated to the particle fragment size. Larger particle size lead to less efficient loading. The material is then transported to the crushers and mills, for which the particle fragment size has a large influence on the energy consumption and the throughput of the mill. The real-time material tracking system delivers optimization potential, taking the ore body characteristic into account. Using the drill rig as a material sensor, information about rock hardness can be used in the prediction of fragmentation and therefore optimize the loading, crushing, and grinding of blasted rock. Let's look closer into the production phase, starting with the drilling. Epiroc drill rigs generate geomechanical information with centimeter scale quality along the boreholes. After suitable spatial interpolation and averaging of the data, one set of data is stored in a material tracking database directly with the corresponding position of origin, whereas another set of data with rock geomechanics and borehole position data is used together with explosives initiation parameters to predict the resulting size distribution of the blasted rock. If required, the blast plan is updated in order to get homogeneous fragmentation result, and the predicted fragmentation parameters thereafter uploaded to the material tracking database. After the blast, a measured fragmentation value assigned to a position may also be uploaded to the material tracking database and related to the predicted result. In this way, the rock geomechanics as well as the predicted and measured fragmentation can be used for real-time optimization of loading, crushing, and grinding. In addition, a mid to long-term analysis and reconciliation is enabled by backtracking downstream results to upstream parameters. As an example of the value enabled with the fragmentation prediction and material tracking, we have used typical data for the drilling and blasting activities in the Aitik mine and predicted the fragmentation result for 2 different rock types present in the mine. The results show that the rock character alone can be responsible for a 50% larger particle size. This corresponds to 15% lower shovel fill factor, a 50% higher crushing energy, and a 20% lower throughput in the mill. Due to the corona restrictions, field testing in Aitik, which was planned, has not been performed as part of the project. The aim with the planned field test is to validate the prediction model and the methodology to track material as part of the excavation process, which show very high optimization potential. Thank you for listening.
Digital twins with distributed particle simulation for mine-to-mill material tracking. Natural variations in the ore body make mine-to-mill optimization difficult. Variations propagate in a complicated way and add to the full system dynamics. Material tracking along vehicles and conveyors can be done with high precision. However, chutes, silos, and stockpiles create blind spots in the tracking. We explore adding distributed particle simulation to the tracking system. For each physical asset that transforms the material, there is a virtual asset updating a digital representation of the material. Services for data storage and analytics are added. With a particle representation, tracking capabilities come automatically. Each simulated pseudoparticle represents a large collection of real particles and have some internal state variables that include mass, position, fragmentation, concentration, and hardness. These have some value from start and are updated at tracking events by the assets using real measurements or simulation. For real-time simulation, we use data-driven model order reduction of DEM. Numerous simulations are run in advance to train a low-dimensional model in predicting the flow in a storage given the control signal and mass distribution. These real-time models we call granular surrogates. Here is a test of integrating a granular surrogate of a stockpile with the ABB control system. The system exchanges information about the material that enters and leaves the stockpile on conveyors. The content inside the storage can be monitored at all time. This simulator is used to test the tracking system before installation. There are two sources, left and right, haul trucks, crusher, and a mill connected by conveyors. Depending on the shape of the pile, material is mixed or flow directly through the storage. If there's a change in the ore properties at the source, this propagates to the crusher and the mill and affect the power draw and throughput. The oscillations here coincides with the truck cycles from the two sources with different ore hardness. Here we show that it is possible to identify the ore hardness from measurement while drilling by tracking and observing the crusher torque over time. It is also possible to predict the properties of the future ore feed for more precise mill control. Finally, we show that using particle-based tracking, it is possible to backtrack the grindability of ore to the precise location in the ore body. With this information, you can decide on a target fragmentation that will increase future grindability. To conclude, particle-based simulation enables material tracking mine-to-mill across processes where no real sensors can see. This makes full system analysis and optimization possible.
This is a system overview for the material tracking service. In the center we have these modules, two modules for the core material tracking service. To this we can assign micro tracking modules, and in the top we can connect visualization analytics modules of different kind. And these storage mix models can be connected to different type of models, FIFO, perfect mixer, or the granular surrogate models. And the example here, we have developed a micro tracking module for conveyors that also connects to the material tracking service and perform and initiate movements of material. And in the top, visualizations of different kinds can be connected. This is a simplified tracking model of the ITIC mine, and containers are storage of different types. Transactions we use for moving material, and then we have materials and properties of these. Properties can be grades, hardness, and so on. So here we can see the containers. configured in the system. This can be configured by any system. And here you can see the algorithms that are used for push, pull, and read contents. And this enables the integration of any model to change this. This will demonstrate how material are moved. Start to pull material from S3 or stope. This is just to show, of course, this is done normally. This is using the fleet management system that initiates these transactions. And we push them to the crusher kid too. And the same method is used for any movement between any containers. On the left there, top left, you can see the current transactions IDs. And these are used to interact with the system if you want to point out a certain transaction. Here we take also from the N6 to blend it, and let's put to the same kid 2. And then we look in, we see that this has been 1160 tons in kid 2, and here we can check the contents. So we see that it's a blend of two materials coming from this N6 S3.
The conveyors in the Aitik mine are connected to the ABB Ability 800XA control system. The control system knows how much material enters, leaves, and is held on the conveyor. To communicate this to the material database, the ABB Ability Ingenious device is used. Ingenious is a small edge computing device used as an advanced processing and communication platform. In this project, a connectivity module between the control system and the material database was developed. This simulated process display shows two conveyors being loaded with material from the crushers and depositing material to a stockpile. The blue level represents the amount of material at a given position of the conveyor. The material flow is divided into discrete samples, here represented by the vertical lines. When a sample has been loaded or removed from the conveyor, a transaction message containing source, target, and mass is triggered in the controller and sent to the Ingenious platform. The data is picked up by the Control System Connect module and forwarded to the Conveyor Connectivity module. The Connectivity module then performs the required operations to add or remove material from the appropriate containers in the material database using its REST API. The material database thus receives real-time updates of material movements from the control system.